all about temperature. Now I'm going to talk about heat. So heat is denoted by the symbol Q. And you got to ask yourself, what are we talking about when we talk about heat? Again, let's use your intuitive sense of what heat is. You say, I have a bucket of water, I want to heat it up. And how do you do that? You put the bucket on top of something else which you think is hotter. And when the two are brought together, somehow the water begins to feel hotter and hotter. So we say we've heated the water, and we say we have transferred heat. Now, people were not sure what really was being transferred. They just decided to call it the caloric fluid. They imagined there was a certain fluid which is abundant in hot things and not so abundant in cold things. When you put hot and cold together, this magical fluid flows from hot to cold, and in that process heats up the cold thing. And they decided to measure it in calories. And so you have to define what a calorie is. And the rule they made up was, we're going to define something called a calorie, where the number of calories you need is equal to the mass of water times the change in temperature. And that's going to be calories. I'm sorry, this is mass of water in grams. If you have 1 gram of water and you did something to it and the temperature went up by 7 degrees, you have, by definition, pumped in 7 calories. If this was a kilogram of water, this will be called a kilocalorie. Okay. Now suppose you say, I don't want to just talk about water, I want to talk about heating something else. Maybe I want to heat a gram of copper. So then you write down the following rule. The amount of heat it takes must be proportional to the amount of stuff you're trying to heat up. That's our intuitive notion. If you've got one chunk of gold that takes some number of calories, you have a second identical chunk. By definition, that should take the same number of calories. If you put them together, it is clear that whatever this calorie fluid is, you need double that. So it's got to be proportional to the mass of the substance. And it's got to be proportional to what you're aiming for, namely an increase in temperature. But this is true for any substance, whether you're heating copper or wood or gold. No matter what you're heating, it is true the heat needed is proportional to the mass and to the temperature. So what is it that distinguishes one material from another? We put a number here, and that number is called the specific heat. The specific heat is a property of that material. And by definition, C equal to 1 calorie per gram or 1 kilocalorie per kilogram for water. Once you've got, so remember, 1 calorie per gram for water is a definition. Once you define water to have a specific heat of 1 calorie per gram, you can define specific heat for other materials by the following process. So what do? You take a container, put some water in it. Let's assume the container has 0 mass. So this water is at some initial temperature T1. And I have some new material, lead, and I want to find its specific heat. So I take the lead in the form of pellets, and I heat the lead pellets to some temperature T2. And I drop these guys into this water. That'll be an example where initially the lead is in equilibrium, maybe on a furnace at temperature T2. Water is in equilibrium, maybe in the room at temperature T1. Then I put the pellets into the water. There'll be a period when the temperature is not defined. Then soon they will settle down to some common temperature called T. We will now postulate, this is a postulate or a law. The total change in Q is 0. In other words, if Q is lost by one body and gained by another body, the loss and the gain must equal. It's the new law. In that case, what can you say in this particular problem? In any of these heat problems, I urge you to draw the following picture. Here is one temperature, here's another temperature, here's the final one, which we don't know. But we can measure, put a thermometer and measure it. Then you say the mass of the water times specific heat of water, which is 1, times delta T, which is the final temperature minus initial temperature. Ditto for the lead pellet. Mass of the lead has got a symbol PB, times specific heat, which I don't know, times the change in temperature, which is T final minus T2 is equal to 0. The sum of all the MC delta T's is 0. This is the gain of heat of the water. This, if you work it out, will be a negative number, because you can see T final is below initial T. This will turn out to be negative, and the positive and negative will add up to 0. So what is it you don't know? Well, you know the mass of the water. Specific heat of water is 1 by definition. T final and T1 are measured by thermometers. Mass of lead is for you to measure. These are known. You can find C. Now, there's a little twist that comes in. I just want to mention that to you. The twist is the following. So I take some ice. Let's take ice, and let me measure. I take this container. I put some ice at, say, minus 30 degrees. I've gone to centigrade now, so we can relate to ice. And I put it on some source of heat. And I watch how many calories are coming in. Let me arrange a device that will pump in a fixed number of calories every second. So as a function of time, I'm expecting the temperature of this to go up. In every second, I get some number of calories. And those number of calories are going to produce for me MC delta T. M and C are constants, so delta Q is proportional to delta T. But if you divide both by the time elapsed, then the rate at which the temperature rises will be the rate at which the heat flows into the system. If heat is flowing at a steady rate, temperature should rise, and indeed it does. But once it hits 0, it gets stuck. I know heat is coming in, but it's not getting hotter. But I notice that the ice is beginning to melt. So there will be a period between here and here. When I pump in calories, I don't get any increase in temperature, but I get conversion of ice into water. And there will be a period when this guy looks like some water with some chunks of ice floating on it. And until all the ice is converted to water, the whole system is stuck at that temperature. Then you can ask, okay, what penalty do I have to pay? That's called the latent heat of melting. And again, I know only in calories per gram is 80 calories per gram for water. Some of your delta Q now goes not to raise the temperature, but to melt some amount of stuff at the latent heat of melting. That's how much Q you need to melt that amount of stuff. And the L varies from substance to substance. For water, it's 80 calories per gram. Then once everybody has become water, then that uniform system of water starts growing. And this is called a phase change. A phase change is when it changes its atomic arrangement from a regular array, for example, that forms a solid, into a liquid. In a solid, everybody has its place. You can shake around where you are, but liquid, you can run around. The specific heat of ice is not the same as the specific heat of water. So you've got to be careful. Even though it's still made up of water molecules, the calories needed to heat 1 gram of ice is roughly half what it takes to heat 1 gram of water. So in these problems, don't make the mistake. Okay, then you go along, and I guess you know what the next stopping point is. When you come to 100 degrees, again it gets stuck till everybody vaporizes, and then you get steam. Then you can have superheated steam, which is at even higher than 100 degrees. So there's a latent heat of vaporization. So you can, if I tell you I took some ice at minus 30 and I dumped in 5,000 calories, where will it end up? You got to first spend a few calories going from here to here. If you got some more money left, you can start melting this. Maybe you'll run out of stuff there, then that's what you will have. Some amount of water and some amount of ice. If you got even more calories at your disposal, you can melt it all and start heating it. You may come this way and you may be running out of calories. If not, keep going here and there and there. And you may end up there if you got enough calories. Or one can ask a question, how many calories does it take to convert ice at minus 30 to say water at 100, you will have to heat. You'll have to do the MC delta T for that, M times the latent heat for this, MC delta D for that, and M times latent heat of vaporization for that.